So thanks everybody for coming to the March 2022 meeting for the Astronomy Fundamentals Special Interest Group. This month we are having a presentation on a follow-up presentation on star classification. This one will be talking about stars other than those that are on the main sequence and their variants. If you would like to have access to the content, the presentation or recording from the part one of this, please send me a message at fundamentals@tucsonastronomy.org, and I will work on getting that to you as soon as I can. I would also ask, I'm in desperate need of some volunteers for content for April and May. I would very much appreciate if anyone is interested in giving a talk on it can be anything you want. Just shoot me a message, let me know. You can also, if you are interested but don't have a topic idea, you can also reach out. There's a couple of items that we had talked about from previous meetings that some members were interested in, such as the history of large telescopes, but more in depth on the moon and some of its craters, and for those of us who are binocular folks, an overview of astronomical objects that make good fit for binoculars, as some suggestions that have been talked about in previous meetings. So,
Connor, do we have any constellations left?
let me pull up that sheet real quick.
Yeah, I think
we don't have many.
Yeah, it's like 4 or 6. I know Doug knocked off a couple 2 meetings ago.
But we're updated. That's not the spreadsheet. Yeah, so we have Volans, Horologium, Octans, and Pavo as the last of the constellation. And wait, yeah.
Those are all southern hemisphere.
Yes, they are all southern constellations. I think Pavo is one that's partially visible from Tucson, but the other 3 are most certainly southern hemisphere only constellations. But outside of those 4, we will have, once we get those 4 done, we will have done every constellation in the night sky. Unfortunately, I don't have presentations for all of them, but we will have done all 88 constellations over. So if you are interested in giving a talk on any of the constellations of the 4 that I just mentioned, please feel free to reach out as well. Could always use some help and volunteers for this. And where is share screen?
And are we going to start repeating after that?
We've talked about in the past in a couple of other sessions of switching from doing like instead of a constellation of the month, an astronomer of the month, to highlight an astronomer of note, like Edwin Hubble, and contributions that they have made to astronomy. They could either historical or contemporary. That some just an astronomer that contributed to a topic that people find interesting. I want that screen.
Okay.
So that has certainly been something that we have talked about. I don't think we have. It's hard. I haven't had anyone volunteer for a particular astronomer at this point. But that is also on the table if you're interested and don't want to do a constellation. Okay, is everyone able to see my screen now? You should be seeing PowerPoint. I can't remember if I pressed the right button.
Good.
Cool. Okay.
It's up.
So diving right into it, this, as I had mentioned earlier, in case I missed somebody that just joined, this presentation is talking about stars that fall off the main sequence. Main sequence stars are stars like our sun. They're in the prime of their life, and these are talking about, and so we are going to venture off and talk about all the variants beyond the main sequence, and there are quite a bit, ranging from brown dwarfs, giants, subgiants, and their varieties to our little exotic friends, neutron stars and white dwarfs. So we'll touch a little bit on all of those throughout this presentation, talking about some highlights, some interesting characteristics about them. Some of these you won't be, sorry about that. Some of these are, well, you can only really identify from specialized equipment and maybe out of range for us here on amateur gear. But nonetheless, it's worth knowing about what these are as we peruse the night sky. So last time we had talked a little bit about how stars get have one of several ways that stars have a classification. Most commonly known to remembered by us through the mnemonic, "Oh, be a fine girl, kiss me," for the main what's the word? Stellar classes that all stars get fallen into, and that further subdivided into a couple of other numeric designations that describe not only the color and temperature of the star, but also kind of lump it into a specific category, which is usually designated by a Roman numeral with the star's classification. For example, the sun is a G2 G2V for a main, or it's a G2V or a G2A, I forget which one. For a G class moderate temperature main sequence star. The 8 is used. The 8 will typically be a Arabic numeral to denote temperature, while the other class, which is what we're going to focus on tonight, is a Roman numeral, which designates what subtype the star is. So putting those Roman numerals into pictures, this is our good old friend, the Hertzsprung-Russell diagram, which is just a fancy chart showing how stars group together depending on their color, their temperature, and their luminosity. And as you can see a little bit more on this right-hand picture, do I have a laser pointer? Okay, well, I can't find it. I'll look for that later. But as you can see in this right-hand picture, it's showing clearly where the number of numerals fall to designate hypergiants, subgiants, giants, and so forth. The sun, is mentioned previously, is a main sequence star, and it fits right around. If you can see my mouse, it might be very difficult just because I can't find the laser pointer function in PowerPoint at this moment. Kind of following low center of this diagram along on the main sequence in this V class. So to start off, we're going to start with brown dwarfs. Brown dwarfs are actually not quite stars. These are gas giants that could not collect enough mass during their formation in order to trigger nuclear fusion. These stars were first predicted by an astronomer named Shiv Kumar in the 1960s, and it took us around 18 years to identify the first one, which was cataloged by E.E. Becklin and B. Zuckerman in 1988. But astronomers, being cautious types, it took them about another 10 years to actually confirm or narrow down that yes, what Becklin and Zuckerman saw was in fact a brown dwarf. This first brown dwarf, if you can believe it, is in the constellation Boötes, and is designated GD 165b. And if you are happening to be out around 11 o'clock tonight and have good skies, you'll actually get to see Boötes as it starts cresting at night over in the east. So if you think you can take a stab at it, go for it. Most brown dwarfs, oh, I think I'm jumping ahead of myself on my slides. After that first contact, that first identification by Becklin and Zuckerman, there was a follow-up detection in 1995 made by Srinivas, I apologize for butchering that name, Kulkarni, which was designated Jalise 229b. And this particular brown dwarf was located in the constellation Lepus, which is in a Lepus or Lupus. I get those two confused because they're off by one letter. Lepus is the rabbit, right?
Yes.
Yeah. Which I believe is in a setting position because it's over here near Orion in Sirius at this time of year. And it's setting at this time of year. Our current estimates peg it that there are anywhere between 25 to 100 billion brown dwarfs in the Milky Way galaxy. It is the second most common type of stellar object that we can find, that we know about. The most common being, red dwarf stars, main sequence red dwarf stars, like Proxima Centauri. So there's about one brown dwarf to every 6 other stars. So it's around, I want to say 18%. On that particular figure. The International Astronomy Union considers any object that has a mass range between 18 to 30 Jupiter masses as a brown dwarf. So these are significantly more massive than Jupiter in terms of scale. Interestingly, they aren't significantly more voluminous than Jupiter. So they would be roughly have the same diameter as Jupiter, just because of how gravity and other characteristics function when you have that much mass. These stars are primarily detected by the presence of lithium and methane, which distinguishes them from red dwarfs. Methane in particular is a strong indicator because stars, as they undergo nuclear fusion, will actually burn this convert this methane into other elements within 100 million years of their lifetime. Most of the light that is emitted by brown dwarfs is very heavy in the infrared and or X-ray frequencies. So again, not really much in the visual range that we can see. Maybe if you got lucky, you could see something with the X-ray range, but with atmospheric characteristics, you would be hard pressed for anything in the infrared, just because our own atmosphere is really good at absorbing that wavelength. So these stars, brown dwarfs, while do have some limited capacity for fusion, they don't sustain fusion like a normal star. So they might temporarily go through a level of a burst period of fusioning hydrogen in their core, or it might be a sporadic fusion rather than a constant flow like you would have inside a star like the Sun or Proxima Centauri. One interesting thing that I've learned is that these objects actually form, despite being Jupiter size, they actually can form without a protoplanetary disk. So for those who aren't quite familiar with their planetary formation mechanics, as a star forms, the dust and other material that is around the young forming star that will eventually form planets is called the protoplanetary disk. And brown dwarfs despite being planetaries, can actually form on their own independently. So they don't have to be forming around another star. They could spawn off like their own as inside of a stellar nursery like the Orion Nebula or the Eagle Nebula, but then just fail to acquire enough mass because maybe a nearby supernova pushed too much of the gas away, and the star just couldn't collect enough material before it went somewhere else. And as I had mentioned earlier, despite their larger mass than Jupiter, these brown dwarfs would actually maintain roughly the same volume. This is primarily due to an effect called electron degeneracy pressure. We'll talk more about that particular element here later on when we start talking about white dwarfs and neutron stars, because it's a very important little piece of physics and understanding those particular objects. So give me a second to remember what I'm talking about here. So as mentioned on the last slide, when we were trying to detect brown dwarfs from other stars, astronomers look primarily for the presence of lithium or methane. And as one of the telltale signatures for it, the presence of lithium comes brown dwarfs typically have a larger amount of lithium in their signatures compared to other stars, mostly because as other stars undergo fusion, the high energy environments that present when these actually takes the helium and will convert it into not take the helium, excuse me, will take the lithium and convert it into helium as a byproduct of the nuclear fusion and nuclear decay that goes on with these stars. And this is done as lithium atoms would get struck by stray neutrons found within the star, and these would then decay into helium, as how this general physical process goes. This lithium evaporates from the star essentially after about 100 million years, and brown dwarfs don't get hot enough to trigger this reaction, so hence this as a really strong signature that when you find a lot of lithium in an object, you're probably looking at a brown dwarf. So the other signature, as we kind of mentioned, was methane. Any store like a red dwarf or hotter is too hot to actually form methane. Methane is a very volatile chemical compound. It degrades easily in the presence of high temperatures. And so the presence of methane around a high mass object, or a very infrared bright object, is also a good telltale signature that what you're looking at what a professional astronomer is looking at may be a brown dwarf. Before we move on from brown dwarfs, is there any questions, comments?
Yeah, Connor, one question. This is Pete. In order for the brown dwarfs to be detected, they have to give off radiation. You talked about infrared and X-ray. How is that energy, or how is that radiation manufactured? Is it in the electron degeneration activity?
No. So electron degeneracy pressure is really just a repulsive force.
Okay.
It's the simplest way to put it, which we'll talk more about later. And I will get horribly wrong because it's a complicated thing to wrap your head around, and I tried to keep it very
Yeah, I don't want to get down into the weeds too much. I was just wondering if there's a simple answer to that.
Electron degeneracy pressure is essentially, you can think of it as that force that keeps your hand from falling through your desk. So it's just that natural repulsive force of electrons. So it doesn't come from that. The infrared comes from the these objects are very massive, and so they're like very warm because they're trying to trigger fusion, but they don't have enough mass to sustain it. So that infrared heat, the infrared light that we're seeing, is just the byproduct of all this very hot material. It's kind of like in the core of our
Oh,
planet.
okay.
The pressure itself of our own core, there's so much stuff on top of it that itself radiates heat. So that's where the
Right.
infrared
Are the
comes from.
cores generally going to be hotter than the outer part of brown dwarf? Well, we don't know that.
I don't know off the top of my head.
Okay.
I would suspect yes, because that's trying to generate fusion, and like as any object, as your pressure increases, your temperature goes up. It's just one of those things that's part of the ideal gas law. And so as you get farther away from this core where the pressure is less in the atmosphere of a brown dwarf, you're going to have lower temperatures. So but for the X-rays, I can't remember from when I was researching this presentation what actually is the main emitter of X-rays in these. I think it comes from the partial fusion that goes on, but I could be mistaken.
Okay. No, thank you.
Any other questions? Okay. Moving on from brown dwarfs near the bottom of the diagram, we're gonna take a little bit of a leap up and move into the subgiants, which is a branch of stars that are more voluminous than our sun. These objects were first described in the 1930s to explain what was known as a luminosity gap between the giant branch, which we see here in this in the HR diagram here with the 3 and designated by Roman numeral 3, and the main sequence dwarfs. So they were noticing that there was this gap in our experimental diagram, and they were wondering, well, what's going on here within this gap, and why is it there? Is there anything that could persist in there? So these objects are as a main sequence dwarf, ages over its time. Particularly light ones will first transition into a subgiant phase. More massive main sequences will transition into giants and supergiants, which we'll talk more about later. But during this transition, gravity will actually alter the spectra emitted by their stars, by their host stars, and a telltale way that allows us to distinguish a subgiant from a main sequence star, which normally when you're looking at just color, temperature, and luminosity, it may be very difficult to distinguish a main sequence star from a subgiant star without looking more at a more detailed view of its spectra. As I briefly mentioned, this is also, subgiants are the next step in the evolution of a low and intermediate mass main sequence stars. The sun itself will transition into a subgiant here in I think it's like 1.6 to 2 billion years, and then it will eventually, the sun will transition and finish up its life as a white dwarf. I thought I had more on subgiants. I must have known that. Moving on from subgiants, we have normal giants. Normal being, a very ambiguous term. These are a little bit more easier to detect than their subgiant counterparts. Because these stars are much larger and brighter. They have a significantly higher luminosity, which is one of the main signals we use to distinguish these. In addition to spectra, these are also a post-main sequence star, and they are notably devoid of all hydrogen in their core. So stars with a low amount of hydrogen in their spectra are one of the key things that we look for when, in addition to luminosity, when identifying these objects. Generally, a giant is not massive enough to trigger fusion of the helium that it has accrued as it burned through the hydrogen in the core over the course of its time on the main sequence phase. They differ from, which differs slightly from for supergiants, which because of their significantly increased mass are actually able to take this helium and convert that into other heavier elements. So these ratios of helium and hydrogen are used to help distinguish very high luminosity giants from very low luminosity supergiant stars. Giants typically have a radius or a diameter of about 10 to 100 solar radii, and are typically between 10 and 1,000 times more luminous than the sun. So they are throwing up anywhere between 10 to 1,000 times more energy as we collect than our sun. 10 to 100 solar radii would probably put most of these objects, if you were to replace the sun with a typical giant, the surface of that giant would easily extend past the orbit of Mercury. On the small side of things, on the larger side of the giant phase, you could easily wind up being something well beyond the orbit of Mars, which is where projections place the sun. When it transitions into a giant, it will, as its volume increases as part of this transition period, it will swallow the Earth and presumably Mars in some simulations. These stars grow really big really quickly. Depending on how much mass is in the original main sequence star before it transitions into a giant, there could be enough mass that it actually continues to transition from a giant into a supergiant. Yeah, the exact mechanics of that kind of vary. There's a lot of factors in play, mostly how much mass is in the object. And then once a giant has exhausted all of the remaining fuel into it, it's no longer able to, has exhausted all of its remaining fuel, and it can no longer withstand, and the pressure in the core from fusion is no longer able to resist the crust, the pull of gravity. The star will then settle down into a white dwarf, ending its life there. So kind of painting that into some more pretty pictures. This diagram took me a little bit to get my head around for it, but the red line on this is a part of the Hertzsprung-Russell diagram showing the main sequence. And the black lines that we have spidering off are showing how a star at 3 solar masses, 1.5 solar masses, and so on, will move off of the main sequence phase and transition into the giant phase. So like here, for example, here in the 1 solar mass, it will abruptly go off and increase its luminosity. Well, also, so up and down is luminosity, left and right is color and temperature. So here, for example, at 1 solar masses, we get an increase in luminosity, but no change in temperature. And then we have a temperature change, and so on. Let me collect my thoughts here for a second. Yeah. So so the numbers, excuse me, it's been a while since I looked at this diagram, are indicative of how long it takes for a star to hit that particular point in the transition. So for a sun-like star, it may take about 11. That doesn't seem right. It may take around 11 billion years, which I think there might be an error in this diagram, because I would not expect this to take our sun to hit. It's not going to have a lifespan of 11 billion years to hit this phase. So I think there might be some small errors in this of how long it takes that star. Oh wait, no, that was what confused me. So this is the star's. I think this was like the star's total lifespan, from the time it entered the main sequence, which for us would have been 4.5 billion years ago, to the time it reached this specific point. So it's basically not how long it takes once it's on the main sequence to get here. Sorry, once it's about to exit the main sequence, how long it takes to get there, but it's basically from year 0 to death instead of middle age to death. That's what confuses me about this diagram. Excuse me 1 second. So Doug was raised a question on one of the previous slides where I was talking about correcting one of my measures, stating specifically that about the distance to Mars is about 150 solar radii, and that
Probably more than that.
so there might be a little bit offset in my number here, but I do recall from several articles that I've read over the years that the expectation is that the sun will, as it transitions into a giant, could potentially swallow Mars. And since the sun is not massive enough to become a supergiant, there might be some wiggle room in that number. Going back, come on. Yeah. Where was I? So any questions on this diagram? Because it took me a while to wrap my head around it the first time. A lot of silence. It's very concerning. I hope I'm not losing people.
Sorry. I'm really new to this, so I'm not sure how do stars start out in one place, just like, presto magico, here I am at one particular place on the scale, and then they change from there.
So actually, that's an excellent question. Let me transition back into a little bit more of a friendlier picture to talk about that, rather than that, Owen. So stars are born in not typically, almost always inside of a nebula, a specific type of nebula called a stellar nursery, which is basically just a ginormous cloud of mostly hydrogen, usually trace amounts of other elements like, say, iron, for example. And to form a star, elements of this nebula will collapse down into thick nodules, essentially. And that gas will then start clumping together to form the star. That's the abbreviated version. Depending on the amount of material that was close to where the star was when it was forming, and how quickly it's able to gather that material, is the main factor that dictates how massive a star gets. And all stars will eventually, once they've formed, they've entered what's known as the main sequence, which is where stars will spend the majority of their lifetimes, which is where we fall in here on the first part of this diagram, is here on the main sequence.
Okay.
So
because I was looking at the Orion Nebula, where there are new stars being born. Okay. I'm getting a little closer to understand.
So if you know the trapezium inside of the Orion Nebula, it's those 5 or 6 really, really bright stars in the center. Those are O-class stars. They're down here far in this, on the left-hand side of this diagram. These stars, so they as you go from right to left, the lifetime of the star decreases. So red dwarfs have very, very long lifespans, on the order of trillions of years. And as we move farther left, O-class stars will have a maximum lifetime 10 million years tops before they transition off the main sequence and go, into a supergiant phase or just go straight into a supernova.
Oh, okay. Thank you.
Yeah, and so continuing on with a little bit more about the physics of giant stars. So you start with a main sequence star that has run out of hydrogen in the core, and the pressure that results from the fusion explosion, essentially, the stars are essentially a continuous explosion within their cores. They've exhausted all their fuel and are no longer able to fuel this explosion, and the star will then begin to contract or collapse in on itself. This collapse has some very interesting physical characteristics, and it actually results in a transfer of energy from the star, because the outer layers of the star are pushing in. So they're basically squeezing in the rest into the core of the star, transferring energy, which causes a bunch of shock waves to go off inside, and increases the pressure and temperature here, and it causes these outer layers that are not quite near the surface of the star. They're still inside the star, but outside of the core. Those inner layers, if you think of the core of stars as like an onion, you have this solid ball that's this core of helium, because the star has run out of hydrogen in its core. It's mostly helium now that it can't fuse. And around that helium core, and I have a picture coming up to kind of explain this here in a second, I think. Oh, that might be in a slide or two to better visualize this. But around this inert helium core, the layers around that will then start to fuse. Because the surface area around the core is much larger than the core itself. This is the characteristic that gives giants more luminosity, more brightness compared to the original main sequence star. That's a little bit of a mouthful, right? Where's that picture I have? Is that before I move on? There it is. I'll go back to the previous slide. I should have moved this particular one further up. So over here on the left, we have a typical main sequence star, much like the sun. It has this core here, it has exhausted all of its hydrogen and it's no longer able to undergo fusion. And so this will start to collapse in on itself. And during that process, you have this essentially inert helium core here in the center. And then this area around the core, once it transitions into a red giant phase, is what's going to start undergoing a fusion process, which is what keeps the star from collapsing further in on the helium core. And as you can see, the outer layer of this, it's typically called the hydrogen burning shell. This outer layer of the shell is much larger compared to the inert core that we originally started out with. So they have a more surface area to undergo fusion, and thus more light is emitted by the star once it enters this phase. So a little bit of a lot of mouthful of physics to digest. Any questions? Because I know I lost some people in there. I must be doing a really good job tonight.
So I have a question.
Go for it, Vance.
In one of your sentences there, you said that the giant stars had used up all their hydrogen, but not all, right?
Yeah, so they've
still fusing hydrogen.
Yeah, so their core itself, excuse me, let me think about how I want to phrase this. So stars themselves are typically mostly hydrogen by volume. But the portion of the star at any given moment that's actually using that hydrogen is located at or near the core. So the way you'll often hear is expressed is that these stars have run out of hydrogen, which is what I did earlier. More specifically, they don't have any more hydrogen left in their core. So they're not fusing hydrogen in their core, but they may be fusing it elsewhere in the star. Exactly where in the star can depend. As star masses increase, it changes. This hydrogen burning shell actually can get farther and farther away from the core. So for in very large massive stars, for example, you might have a layer of carbon fusion around. You might have you might have a core made almost entirely of carbon, and around that carbon core is a layer of helium fusion, and then farther out from that is a layer of hydrogen fusion. Depends on the mass of the star. And some other characteristics, but typically when
More complicated than we thought.
sorry, can you say that again?
So that's more complicated than we thought, and I mean a long time ago, I guess. And that's really the supergiants are the ones that are running through various elements to fuse as they go to the final stage. Is that true?
On
Yes.
the onion skin. Oh,
So it's helium, carbon, until it gets
all
to
the way
iron, and
up
that's
to where you have a core of iron.
so once it gets to iron, then it can't
Fusion
fuse it.
stops.
Everything collapses quickly.
Well,
But
not necessarily. It's just that is usually the highest number element that the stars can fuse. Usually the other elements come from other processes like supernovas.
Yes.
So to delve into that a little bit more, iron is a very interesting element in that when you take two elements and fuse them into iron, that process does not give off. It's a neutral energy gain. So you use as much energy to fuse the iron as it gives off. So you have a net zero energy gain essentially, and that energy gain, and a fusion process in a star, you want to have an energy gain. You want to give off more energy than you use for the fusion, because you're trying to generate an explosion in order to keep yourself from gravity from crushing you. So when you fuse iron, there's not enough energy to resist gravity, which is what triggers stellar collapse. I've seen a lot of differing estimates in terms of, once a star begins to fuse iron, how long it has left to live. The main driver is typically how much mass. I've seen one estimate that said like, within, a couple of minutes of starting to fuse iron, that the star goes supernova. I've also seen, we also know of stars that are a little bit significantly older than that still have large amounts of iron in them. So the exact timeline, I don't really have a good always this estimate of saying, once I have iron in my star, how long do I have left to live? It's very conflicting on that particular topic. But I think it was either as Doug or as Peter mentioned, every element beyond iron that we see is not a byproduct of nuclear fusion inside of a star, but rather a result of a supernova explosion of various types.
I have another question. Is there something between the core and then this outside shell? Just a layer of, I'm not sure what, or there's a space in between?
No. It's layers of different materials.
Yeah.
Oh, okay.
Like if you've got a star that's maybe burning carbon in the core,
Mhm.
using carbon, then that could be surrounded by a layer of material where it's burning helium, and then that could be surrounded by a layer where it's fusing hydrogen, and then that could be surrounded by a layer where of just hydrogen gas where fusion is not occurring. So you could have these multiple layers of material. There's no gap, there's no empty space, so to speak. There's something, it's, the
Yeah.
star is filled all the way from the core to the outer edge.
Okay, great. Yeah, that's what I figured. Okay, thank you.
I mean, most of the substance is plasma, isn't it, Doug?
Yeah, I guess so, yeah.
So it's not, not a true gas, it's not a true solid, not a true liquid.
Until you get to the very outer edges, then it's a gas.
So there was one other statement you made or you had in there that the giants were 13 to however much bigger than the sun or than Jupiter. No, what was the one, the brown dwarf? Sorry, brown dwarfs were as low as 13 times the size of
So,
Jupiter, so it almost became.
a
I
brown
think he
dwarf,
said 13 to 100, 13 to 30 times the mass of Jupiter in roughly the same volume.
Right.
so a brown dwarf will have a mass range of 13 times the mass of Jupiter up to 80 times the mass of Jupiter.
Mm.
Beyond 80 times the mass of Jupiter, the star is actually has enough material to sustain fusion, and it actually becomes a white dwarf star. Not a white dwarf star, excuse me, a red dwarf star.
Thank you.
So Jupiter came close in the
Not that close.
scheme of things.
Has quite a ways to go.
Yeah, but in the universe, talking about the universe, it's darn close.
Yeah, but Connor, as a general correlate, mass generally is going to determine how a star is going to start out. The mass of the initial material accretion. And then once a star has mass, depending on what it is, will determine its position along the main sequence and when it's probably going to transition to other phases, correct?
Correct.
Yeah.
I mean, as far as everything I've read, mass is probably one of the main correlates. There are others, but
Almost determines everything about the star's life, including how it dies.
right.
Yeah. Yep. Mass is the driving factor, and everything about how a star, once it's formed, how long. The mass is the main thing that determines everything else about how that star. So if you know the star's mass, you can basically predict everything else about that star for it's how long it has left to live, what it's going to transition to in terms of post main sequence phases. Will it become a black hole? Will it become a neutron star? All of that you can tell just purely from the mass.
Oh, I've read something about once the star starts fusion and lights up, it blows away most of the rest of the gas around it and stops growing. Is that true?
Yes.
Pretty much.
That's a physical characteristic of what's known as the Eddington luminosity. Interesting fact, that physical law is also the same thing that controls how much material a black hole can consume. It's the same basic thing. Basically, the light emitted by the star creates pressure on the gas as it tries to ball up onto the star, pushing away this gas and basically starving the star of any new material so it can't grow.
So
And that also, although this is not quite on topic with this talk, but that also partially explains some of the theories of planetary formation, why planets typically that are close to the star, like Mercury and Venus and the Earth and what you'd call the terrestrial planets, are not gas giants for the most part. They tend to be rocky type planets like Mercury and Venus, because all the gas has been blown away from the inner part of the solar system. So your gas giants usually reside farther away.
Except for the super hot Jupiters.
Yes, but there's a theory for that too. There's a theory for those.
Yeah, they moved somewhere, and ours, there was something I was watching where ours was there, Jupiter was there, but then Saturn had something to do with it, and it ended up where it is
Just
now.
general planetary formation theory suggests that planets that are close to the star are probably rocky terrestrial types because the gas has been blown off. So that all that's left are heavy dust and rocks to form planets. So the gas giants form in the outer part of the solar system where you still have gas that didn't get blown away.
So the initial, not the size of the star as it ignites relates to how dense the gas was as it was forming.
No, it's just
Because
Yeah.
size, it's mass primarily.
Yeah. So it'd have to go in very quick to make a very large star that then ignites.
If the gas cloud is not very dense, the gas cloud that you're using to form your stars is very thin and not very dense, then you are probably not going to get very heavy stars. You're probably going to get fairly small stars and perhaps a lot of brown dwarfs because there just isn't enough material around to form your larger stars. On the other hand, if you have a very dense cloud, like the Eagle Nebula, for example, that's very dense in material, you can't see through it. It's black dark. You've probably got some fairly heavyweight stars forming inside that nebula.
Another great example of that is the Tarantula Nebula in the Large Magellanic Cloud, which has some of the largest stars by mass we currently know about. In fact, a couple of the stars are actually somewhere on the range of 200 times the mass of our sun, which is a little bit beyond what we thought was the upper limit for natural star formation. So the stars, some of the stars in some of these stars in the Tarantula Nebula are oddities, and we aren't quite sure how they got that much mass to get as large as we think they are. So they're kind of a little bit of an interesting mystery in terms of stellar formation. But circling back a little bit, we had talked a little about mass and how that can be used to decide is the main factor in deciding how a star evolves over its life. But for identifying giants, subgiants, and supergiants, we're primarily looking at a couple of other characteristics besides their mass. Most because a star in the 200 solar mass range could be a very large O-class star, or it could be a G-class supergiant, a yellow supergiant. So looking at mass from our point of view is doesn't exactly tell us what type of star we're currently looking at. We have to rely on, as I mentioned, the star's spectra, but also its luminosity to tell us more about, which type of star we're looking at. And so this equation here, which is the only equation you're going to see in the rest of the presentation, it's just kind of important to communicate this, showing the relationship between a star's luminosity, the star's temperature, and the star's radius, where L is luminosity, R is the radius, and T is the temperature. And showing, we can measure the luminosity pretty simple enough by just measuring how much light is collecting on a photosensitive detector. We can measure the temperature of the star easy enough by just looking at its color. And from that, we can say, well, I know my luminosity, I know my temperature, what's the radius of this star? And I can use those combination factors to then say, I have a star of this radius, I have this in my spectra, this must be a giant, or this must be a supergiant, and so on. So just by using this one formula here, we can, derive the rest of the information we need to help us better catalog what the star is. There's a lot of variations to this luminosity, radius, temperature formula. It depends on how much math you want to get into. This is kind of the more basic one you can look at. But there's others that incorporate other factors like luminosity with respect to mass, or temperature with respect to mass, and so on.
You know where the constant comes?
But Stefan Boltzmann concept pops up a lot when you talk about the physics of gases or large or energetic bodies. You'll see it in things like radio frequencies. It's one of those things like pi. It just pops up in a lot of equations just for reasons. But
So it's probably derived experimentally by looking at it, luminosity and size and all that, and then figuring out what you need to make.
No, the Stefan Boltzmann constant is actually one of those basic constants of physics, like G, the gravitational constant, or what's the one for
the Planck constant?
A Planck constant. It's one of those basic constants that was derived from experimentation and observations, and it has to do with thermodynamics.
Yeah. They experimented, found numbers that work, and it works on everybody.
Okay.
Yeah.
I guess you could say it that way.
Yeah. So moving, come on. So before we move on to supergiants, any other continuing questions?
I'm just wondering, do stars lose mass as they get large, as they age, or do they? Now that we talked about mass is the determining factor.
They do, and I think as we talk more about supergiants here, I do answer that question in a little bit more detail.
I mean, the sun is losing mass all the time right now. It's called the solar wind.
Oh, okay. All right. Thank you.
So moving beyond giants, where's my phone? I don't have my phone. I was wanting to know what time it is. Moving beyond giants, we enter into supergiants, which are starting to get more in the fun part of physics. Fun for people who like really extreme objects. These are where giant stars are for low to intermediate mass stars. Supergiants are the next evolutionary step for massive stars, so anywhere from 8 to 10 solar masses and up. Any star in that mass range will almost always transition into a supergiant phase. They may go through the giant and into supergiants, as we had mentioned earlier, but they may also just, if a star is massive enough, may go straight into supergiants. Kind of varies. Again, mass being our key deciding factor on how that actually occurs. Remind myself what I need to talk about here. So as a very massive main sequence star exhausts all of the fuel in its core that was originally hydrogen, it has so much mass that it's actually able to start fusing the helium that it's accumulated in their core from this hydrogen fusion, and actually start fusing that helium into heavier elements, which in order to fusing helium gives off a lot more energy compared to fusing hydrogen, which in turn greatly increases the star's volume and temperature. No, sorry, I'm getting that mixed up. It increases the star's volume, and as we saw in that equation earlier, we're going to actually reduce its temperature a little bit, change its color some. I might be getting my math terms mixed up here. Let me think about that for a second. Yeah. And you know, as this increase of energy from helium fusion that it causes a volume shift, and it just makes these stars utterly ginormous in comparison. The one of the largest supergiants we know of, which I failed to get a picture of now that I'm even thinking about it here. If you're interested in your own time, just search for VY Canis Major. This star has, I think it's a radius of about 1,000 times that of the sun, which would put, if I remember correctly, puts its outer surface right up to where Jupiter's orbit is. You know, it's just a ridiculously large star. Where am I going next? Excuse me for a second. So once you have this main sequence star transitioned into a supergiant, it's going to go through a helium fusion phase and potentially fuse other elements beyond helium. If the star is massive enough, you can start fusing carbon in its core, and all the way up to oxygen. But eventually, it's going to it's going to exhaust all the fuel that it can, and these stars would then transition into any of the other 3 variants we talked about later. The supergiant could transition into a white dwarf, a neutron star, or a black hole. Differs from giants, which would typically only transition straight into white dwarfs. These stars, and I'll have a picture to show this. I'll explain this last bullet here in the next slide. They move material in their core so efficiently that they're able to actually take hydrogen that's from the extreme outer edges of the star up by where we might say in the star's coronosphere, very near the surface, and mix that material all the way down into the core. So essentially their own size turns them into a really good blender of all this material, allowing them to keep fusing hydrogen throughout the entirety of their supergiant phase until they've been completely, you know, they'll run out of hydrogen and you just keep fusing, as we mentioned, all these other heavier and heavier elements. Pictorially, as a picture, it looks kind of like this. So depending on, if you remember a little bit from high school physics, convective is, you know, that mixing motion that you get like when you're boiling water as cooler material falls in from the surface of your boiling pot and goes near the bottom of the pan before that material that's near the bottom of the pan starts cooling off and goes to the surface, creating this motion of material. The same thing happens inside of stars, but where this convective motion occurs very much depends on its mass. So red dwarfs, like Proxima Centauri, will have convection, this convection of current, moving material all the way from the star surface down to the core. And these are for main sequence stars. For stars like the sun, this convective current has a barrier zone around the core. So the inner core doesn't go through convection. It just radiates energy. But then the portions outside of the core have this convective current. And then in supermassive stars that look like the kind that would transition into a supergiant, it's the reverse, where the core itself is convective, but the outer layers are not. But when these very massive main sequence stars transition into a supergiant, it actually results in a transition from this leftmost picture back into this rightmost picture. Not rightmost picture, the center picture. So we go from having this convective core back to having this convective outer shell. And this convective outer shell is what's pulling material back into the star so it can continue fusion to maintain the star's structure as it fuses heavier and heavier elements. That's a little bit of a mouthful to digest. Any questions that I can answer on that? Because that is kind of a lot of. Okay. Any questions on supergiants before we move on to our next object type? Cool. So moving on, we have Wolf Riot stars. These are interesting objects. So these are typically a follow-on stage to a supergiant star. These objects are very energetic, like every star. But what key characteristic of them is that they are actually violently ejecting their outer layers of plasma into the surrounding environment. So think of it as a star that's just repeatedly sneezing and throwing off all of this gas around it as it tries to transition into something that's a little bit more stable. So these aren't very stable from a physics perspective. They're trying to reach an equilibrium. These will eventually throw off so much material that we will actually see it in the form of a planetary nebula. And in fact, the Crescent Nebula, Caldwell 27 and GCA 6888, which is located in the constellation Cygnus, which will be up very late, very early in the morning, around 2 to 3 a.m. as it rises with Sagittarius, is an example of a nebula, a planetary nebula that was formed by a Wolf Riot star. These objects are predominantly identified by large amounts of helium and almost a complete absence of hydrogen in their spectral lines. But concentrations of other elements such as carbon, oxygen, and nitrogen are used to further give us a little bit more fine-grained control identification of Wolf Riot stars. So you can have Wolf Riots that are heavy in carbon or heavy in oxygen or heavy in nitrogen, and it changes a little bit more about the characteristics of these stars. These stars are incredibly bright. I forgot to put any luminosity metrics for giants and supergiants, and I regret that now. I may have a slide that talks about them here in a second, if I can see that correctly. But Wolf Riots are very bright. They are throwing off anywhere from 1,000 to 1,000,000 times the amount of light as the sun does. And almost all of that light is coming at us in the UV spectrum rather than in the visible spectrum. I need to, excuse me 1 second.
Hey, Connors, Pete, I have a question when you're ready.
Go for it.
Hey, okay, the second you said it continually ejects material out into space. It isn't a continuous stream. Is it more like a pulse and it has a period to it, perhaps?
It's a combination. You might have a very intense pulse.
Okay.
But as Doug had mentioned earlier about how the sun is constantly losing material in the form of its solar wind. Even with a Wolf Riot object, the solar wind is pulling off so much material.
Okay,
Just
so
from
it's
the
more of a
solar wind.
continuous stream rather than a pulsing out then.
Yes, but you would have you'll have both. You'll have a continuous outpouring, but that you might have a large coughing fits essentially.
Mhm. I was
as it-
thinking it could, oh, sorry.
Go ahead, Haiti.
Oh, I was thinking it could be like a car backfiring, something like that.
That's one way to think about it.
Uh-huh. It's an idea.
Where am I going next? So what did I put in the slide? What was this about? So this is a table, courtesy Wikipedia, showing just how widely these stars can vary in their luminosity. These are for a nitrogen heavy Wolf Riot stars, and as you I believe this star here at the bottom of the list, WN5H, yeah, no, R136A1. I think this is, if you recall earlier, we talked about that star in the Tarantula Nebula, which has a solar mass of about 200 times that of the sun. That's this guy down here. So that 200 solar mass star that we talked about in the Tarantula Nebula is in fact a Wolf Riot star. And as you can see, this star is just giving off a lot of energy. You have 5 million times the amount of light coming off of this one star compared to our sun. That's really bright. But you can see here that the Wolf Riots are giving off just so much energy, from 160,000 to 5 million times the amount of light of the sun. They're very, that's just a lot of energy. Let me recall my notes here on the slide. Yeah. So these stars, because of their mass and some of their other physical characteristics, as we talked about in supergiants, that how these stars have a convective motion that goes all the way from the surface of the star down to its core. And Wolf Riot stars, this convective motion is very strong, and it pushes material all the way from its core, heavier elements all the way from its core that have been fusing, say carbon in its core, and is pulling down on these helium down from the helium and hydrogen from the surface of the star and swapping it out with this carbon from the core and pulling that back out. Kind of like how you would have a centrifuge spinning really quickly to separate heavier fluids from lighter fluids. In a sense, that's what's going on inside of this Wolf Riot stars. And as these layers flip in on each other, you have this carbon that's coming up out of the core, or any heavier elements, even then, like oxygen or and so on. This movement of material is what causes the very intense stellar winds, which are just eventually just get ejected off the star entirely. So if you're looking at the planetary nebula around the Wolf Riot star, you will see a lot of these traces of like carbon and oxygen inside of it. Now, as it's losing this mass, these stars will, due to our good friend law of conservation of momentum, creates a feedback loop in the star, where the star, as it loses its mass, will actually start rotating faster, which has an impact on the convection currents inside the star, increasing the strength of these convective currents, and then thereby increasing the stellar wind. So we have a positive feedback loop of star loses mass, star speeds up, star ejects off more mass, and just keeps speeding up and speeding up until the star has, sped up so quickly that it's blown off all of these outer layers of material, and we're left with just the core of the star, which may transition into a white dwarf. I forget. No, I'm misreading my own bullet line. So once the star has blown off all these outer layers, and it's formed this planetary nebula, what's left after this loss of material is what forms the Wolf-Rayet star. Oh, excuse me, that's a bit of a mouthful to think about. Questions or comments? Right, have another.
So, sorry, can I ask another question?
No, go for it.
So is a Wolf-Rayet star, it doesn't start out as one?
No, this is kind of like a next step phase. So once you get from a supergiant, then a supergiant star would transition into a Wolf-Rayet star, depending on how much mass it has. So the supergiant star could also just transition straight into a supernova. It varies.
Okay. I forgot we were on this continuum. Okay. All right.
Yeah. Nope. Excellent question. So moving off of supergiants, now we're getting into stars, the end of life state of stars, which are our good friends, white dwarfs and neutron stars. We won't talk about black holes in this presentation, just because we've done a couple of other topics on them in the past. But white dwarfs are, I think, one of the more common outcomes for the end of life of a star, just because this is the endpoint of low mass stars, like our sun, and those low mass stars are significantly more common than the heavy supermassive stars, which would transition into neutron stars and black holes, supergiants. So these are the more common end state of a star once it's exhausted all of its fuel and reached the end of its life. These white dwarfs are typically the byproduct of stars that had an original main sequence mass of 10 times the mass of the sun or less, that have, they've gone from main sequence, they've transitioned into a giant or a supergiant phase. And while they were on this giant phase, they've lost material from their solar winds, or through other events like well, I can't think of the word at the moment, but there's other events that would cause stars to lose mass when they're on these giant supergiant phases. My throat is really dry. Excuse me 1 second. And they've lost enough material that they just calm down and they settle down into a white dwarf. White dwarfs are very small in volume. They're roughly about the size of the Earth, but with the mass of the sun packed into that, into that same amount of volume. So if you just took the sun, squeezed it down to the size of the Earth, and then put it right there, you'll wind up with a white dwarf star. Excuse me, I need to pause myself and get myself something to drink so I don't ruin my throat. I will be back in really quick.
And he's back.
Is he back? He's back.
Sorry about that. I got up and when I got back, I realized that my internet was starting to cycle and it kicked me
Oh.
off. That was not me hanging up. That was my internet saying, no, I hate you right now. Come back in 5 minutes. Where did I leave off? Am I still screen sharing? Go back here, go back here. Apologies about that. My throat does feel much better now. I need to grab a lodge, use something to drink. How much more do I have left in this presentation? Oh, wow.
Now you're running long.
Yeah. I might end up having to do a part 3 of this and just finish up white dwarfs because it is 8 o'clock and I have another 15 slides to go.
Wow. And some of those look fairly complex.
Yes, I may have to just call it here. Actually, yeah. I'll actually just call it here as we go since we start and pick up next month right at white dwarfs. I think that's actually a good spot to talk about.
Yes,
White dwarfs,
good.
neutron stars, and magnetars are, they're really dense subjects to talk about. And there's a lot of physics that you kind of have to get through in order to kind of understand them a little bit. So I think I will actually save white dwarfs and beyond for next month when I have something to talk about. And
Okay, so that gives you a little more time to find a speaker to pick up after that.
yes. Yeah, wow. It took me an hour and a half to get through that. There's a lot of material in that. So
Well, we interrupted a bunch too and asked questions, so that was good.
yeah, some of the stuff in this is, well, I understand it because I read a lot of astronomy, physics, and research. But making sure you can explain some of the conceptuals on this can be quite difficult when especially because there's sometimes you just have this mental image, and then finding a picture that explains the mental image is not an easy thing to do.
Yeah. I have a friend who before he takes the test, he wants to explain it to me so that he can, it helps him get a better grasp. Or, I mean, this was a long time.
And with that,
That was great.
it is 8 o'clock. I'm going to go ahead and actually just end the recording here.